All right, in this video, we are going to be doing the last section in chapter 6 that we cover, and this is section 6.5, which is the average value of a function. So in this section, we're going to look at a opposite of a theorem that is covered in our Calculus 1 class. In Cal 1, you cover an idea called the mean value theorem. We are now going to talk about how the mean value theorem works for integration. So if f is a continuous function on a closed interval a to b, then there has to exist a number c in the interval a to b such that f of c equals the average value function. So this f sub avg is what we call the average value function. So the average value function can be found by the following. In front of the integral would be the constant 1 over b minus a, which is just the subtraction of the endpoints. Then you will multiply that by the integral from a to b of the function f of x dx. And then once you evaluate this right here, so that's the average value function, there has to be a value c that you could plug into the original function and get that value. Now, there is an alternate definition down here below, which is the one right here my pen's kind of waving at. I don't ever use this formula, so if you'd like to write it down, you can, but we're never going to use it in that form. It's just an equivalency factor in this case. So graphically, here is what the average value of the mean value theorem in integration is. So if you are integrating under the curve between a and b, what you're trying to do and what the average value is it's the y value of the function, where if you found that, you got to find this line. So this value right here, we're trying to find this y value that if we found the area above it and the area below it, they would end up canceling each other. So these two areas right here are equivalent to each other. What the average value allows us to do is allows us to find this by doing integration. So essentially, you're going to find the area under the curve and multiply it by 1 over b minus a. Now, it looks like in this diagram that c is right smack dab in the middle. That's not always the case. Depending on how high or above the average value of function goes, c could be shifted left or right depending on the problem. So what we're going to do here to start off is that before we start solving for the c values and such, let's just practice finding the average value of a function. So given f of x equals x squared over x cubed plus 3 all squared, find the average value on the interval -1 to 1. So as far as the formula goes, the average value function is defined as 1 over b minus a times the integral from a to b of f of x dx, where f of x is given to us in the problem, and also the interval from a to b is also given to us. So if I plug in what I know, this will be 1 over 1 minus a -1 times the integral from -1 to 1 of x squared over x cubed plus 3 all squared. All right. In front of the integration, that's going to end up becoming a fraction of 1/2. And now, as far as integrating this function, it looks like the best way to attack this is going to be use substitution. So up here, kind of out of the way, if I let u be the inside function, which is x cubed plus 3, then I can say that du is 3x squared dx, and therefore du over 3x squared is my dx value. Now, since I'm doing use substitution, I need to also change my parameters. So the a and the b need to be plugged in for x to set my new parameters. So -1 cubed is -1, and -1 plus 3 will give me a lower parameter of 2. And then plugging 1 in for x should give you an upper parameter of 4. And then this will give me x squared over u squared times my dx term, which is du over 3x squared. Just like I wanted to, the x squareds will cancel. You can factor that extra 1/3 out to the front to make it a 1/6. And then we're going to integrate from 2 to 4, and I will rewrite 1 over u squared as u to the -2 du. I can now integrate this function, so it would be 1/6 times, add 1 to the power and divide by the power, and evaluate that from 2 to 4. I'm going to rewrite this a little bit to make it a little easier on ourselves. So I'm going to bring that -1 out front to make it a -1/6 in this case. All right. And then I am going to end up, going to write this as 1 over u. Evaluated from 2 to 4. Sorry, I thought I wrote a number down wrong. I was double checking myself. Apologies for that. All right, so plug your numbers in. So this would be -1/6 times 1/4 minus 1/2. All right, so 1/4 minus 1/2 is going to be a -1/4. And then multiplying these two fractions together would give me 1 over 24. And that is the average value of this function. Now from there, we could try to solve for a C value, but that's not really needed right now. We'll get into that in just a few minutes once we do a couple more practice problems. All right, any questions on that first one? All right, so let's do a second one. We're going to find the average value of the function h of x equals cosine to the 4th of x times sine of x, this time on the interval 0 to pi. So this is the exact same idea. The only difference is that you may want to call this h average, so because it's the average value function of h. So in front of your integral will be 1 over b minus a. So that's going to be 1 over pi minus 0. We're going to integrate from 0 to pi of cosine to the 4th of x times sine of x dx. All right, so just like the last one, it's very similar, only you're doing this in terms of trig, where you're going to get a 1 over pi in front of your integral. And then the easiest way to integrate this function is going to actually once again be u substitution. So I'm going to let u equal cosine of x, because that's what's being raised to the power. So du would be negative sine of x dx. So therefore dx would actually be du over negative sine of x. Once again, I need to change my parameters. So I'm going to plug the 0 and the pi in for x to get my u parameters. Cosine of 0 would be 1. And cosine of pi, which would be -1. Those are backwards, but we'll fix that in just a minute. This would be u to the 4th times sine of x times dx, which is du over negative sine of x. Very nicely, two things I can do here. Number one, the signs cancel, and then I can factor that negative out to the front and make it -1 over pi times the integral from 1 to -1 of u to the 4th du. Now, since my parameters are backwards, we can flip our a and b parameters here if I put an extra negative out front. So I can write this as 1 over pi times the integral from -1 to 1 of u to the 4th du. And now it's set up for a pretty easy integration. This would be 1 over pi times, add 1 to the power, divide by the power. So u to the 5th over 5 from -1 to 1. I'm actually going to factor that 5 out front because I don't really need it in there. So make that 1 over 5 pi. And then if I evaluate just the u function at my parameters, this would be 1 to the 5th minus -1 to the 5th, which would come out to be 1 over 5 pi times 1 minus a -1. That's going to be 2, and when you multiply this together, you get a final answer of 2 over 5 pi. And that is your average value of this particular function. All right, so let's do a third one and then we'll go on to something else. So find the average value of the function on the interval 1 to 5 if h of u is defined as the natural log of u divided by u. All right, so once again, setting this up as our average value function. So we're doing h. So once again, I will call this h, the average value of h would be 1 over b minus a. So this is going to be 1 over 5 minus 1 times the integral from 1 to 5. All right, and then we're going to plug our function in, which would be the natural log of u over u du. Now, once again, this is going to end up being what we normally call a u substitution because we have a natural log involved. But since the function is already in terms of u, what I'm actually going to do is I am going to do an x substitution. So I'm kind of going to go backwards a little bit. So I'm going to let x equal the natural log of u part. So therefore, dx would be 1 over u du. And I could say that u times dx is my value of du. So once again, I'm only doing this opposite because they already did u, so you can't really do a u substitution for a function of u. So we're going to go backwards. In front of my integral, that you should end up with a 1/4. You still must change your parameters. So plug the 1 and the 5 in for u to get your new parameters. The natural log of 1 is actually 0. And then the natural log of 5 is nothing we can do easily. So we'll just leave it as ln of 5. Your ln of u becomes x over u times your du term, which is u dx. Very nicely, my u's cancel, and I'm left with a pretty nice integral of 1/4 the integral from 0 to the natural log of 5 of x dx. So add 1 to the power and divide by the power, and you should get x squared over 2, evaluated from 0 to the natural log of 5. If I factor that 2 out like I did a couple problems ago, I actually did on the last problem, actually, that would be 1/8. If I plug ln of 5 in, that would be the natural log of 5 all squared minus 0 squared. And since the 0 is just going to go away, your final answer here would be the natural log of 5 all squared divided by 8. And that's going to be the average value of your function. All right, now that we have practiced doing our average value, now we want to go the one step further and finish off the mean value theorem of integrals. So for example, number 4, find the average value of the function on the interval 0 to 2, and then tell me the value of c that makes the average value equal the original function. So now we're going to find that c value in the interval where the average value actually exists at. So first thing you got to do is you got to find your average value function. So that's going to be the exact same thing we just did. So average value of f would actually end up equaling 1 over b minus a, so 1 over 2 minus 0, times the integral from 0 to 2 of, let's see, that's going to be x plus 1 all cubed dx. And if you haven't noticed yet, a lot of these are going to end up being u substitution. It is not always true, but a lot of them do work this way. So I'm going to let u equal x plus 1. And the good thing about this is that we get a direct of du equals dx. That doesn't happen very often, but we'll take advantage of that. So working my way down, this would be 1/2 the integral. Plug your old parameters in for x to get your new u parameters. And 0 plus 1 is 1. 2 plus 1 is 3. And then you just get u cubed du. This will be 1/2 times, add 1 to the power, divide by the power, which is u to the 4th over 4, evaluated from 1 to 3. I can factor that 4 out front to make this a 1/8, and then inside the brackets, you will have 3 to the fourth minus 1 to the fourth. So this is 1/8 times 81 minus 1, which is 1/8 times 80, which means we have an average value equal to 10. Now, according to the mean value theorem of integrals, there should be a value in between 0 and 2 such that the average value equals the original function at c. So I'm going to take the original function, which is x plus 1 cubed, and I'm going to replace it with a c. And then I'm going to set this equal to the average value that we just found. And we're going to solve for c here. If you take the cube root of both sides, c plus 1 would equal the cube root of 10. And then subtract 1 from both sides, and we can see that the value of c that makes the mean value theorem true would be the cube root of 10 minus 1. And once again, we don't have a calculator or anything, but by deduction, we could figure out that that is between 0 and 2. So that's the only extra step we really haven't been doing, is just setting the original function equal to the average value, and that should be somewhere in between 0 and 2. All right, what if we change it up a little bit? What if I tell you what the average value should be and you've got to find another missing part? So example number 5, find the numbers b such that the average value of f of x equals 2 plus 6x minus 3x squared on the interval from 0 to b is 3. So you've got to find every single b value, because there could be more than one based on the instructions. Find all the b values that will make the average value of this function equal 3 exactly. All right. So first thing I'm going to do is I'm going to find the average value function. So average value of f would be 1 over b minus a. Now, since b is not known, this would actually be 1 over b minus 0 times the integral from 0 to b of my function. All right, no use of this time. This is going to be just direct integration. So that would be 1 over b times, you can integrate all three of those terms and be 2x plus 3x squared minus x cubed evaluated from 0 to b. All right, plug your parameters in. This would be 1 over b times, if you plug b into all of those terms, it would be 2b plus 3b squared minus b cubed. And then technically, if you were to plug 0 into all of those, you would just get a bunch of zeros. Take the 1 over b that's out front, and you can distribute this to all three terms, and you will have your average value of the function. So your average value would actually just be 2 plus 3b minus b squared. So there's the first part. But our question is, what value of b needs to go in here for it to equal 3? So now you're going to have a new problem. So I'm actually going to rearrange this a little bit. I'm going to write this as negative b squared plus 3b plus 2 needs to equal 3. So the only way to solve this is you're going to have to set it up to be factored. And usually you got to factor it. It has to equal 0 on one side. Now, to make the factoring a little bit easier, I'm probably going to try to make the squared term positive. So I'm actually going to move all three of these terms over to the right-hand side. And I should be able to write this as a 0 on the left. And then on the right, you'll get a b squared, a minus 3b. And then when you bring the 2 over, you pick up a plus 1. While that doesn't factor very nicely, that's okay. You can still do your quadratic formula to solve for b here. So b would equal the negative of your linear term, so that's the negative of a negative 3, plus or minus the square root of negative 3 squared minus 4 times a value times your c value. All of that divided by 2 times a. So this will come out to be 3 plus or minus the square root of 9 minus 4, all divided by 2, which comes out to be 3 plus or minus root 5 divided by 2. Now, those are your two possible answers. And if you're double checking the original interval, the only restriction here is that b must be bigger than 0 because it's the upper parameter. And if you double check, root 5 is less than 3. So whether you subtract it from 3 or add it to 3, in the end, both of these are going to be positive results. So they are both answers. Now on your homework, there is no plus or minus button, so you may have to individualize these. So you may have to write them distinctly as 3 plus root 5 over 2, and then your second answer would be 3 minus root 5 over 2. But both of these b values, if you checked, would give you an average value of the original function to be exactly 3. That ends the video for 6.5. This is a very short section and a little bit small topic we had to cover. That also ends chapter 6. In the next video, we will begin chapter 7. I believe the next section is called integration by parts.